So I've got 11:01. I'm going to go ahead and kick things off here, and I expect that we'll have some folks join us as we move along, but time is short, and I want to make sure that I give Dr. Mersbacher enough time to go through the main part of this session, which is really going to be her talk about quantum. So I'm going to share my screen. Hopefully everything will work well here, and we can get going. Let's see, hopefully everyone can see that okay. Let's see, I'm going to assume you can. And Celia, I don't think I can hear the attendees, but if you notice, okay, if you notice something going off kilter here, please let me know. So first, I want to thank each of you for attending our session today on titled From Crystals to Quantum, Envisioning the NCFL of the Future. And this is really the NCFL, just so that we get that acronym down because I use it a lot, is the Nanoscale Characterization and Fabrication Lab. And I'll tell you a little bit more about that in a moment. I'm speaking to you. I have a couple of different hats that I wear that the CRC folks know me. They know me as CEO of NanoSafe, but I'm speaking to you today in my day job as a research scientist at Virginia Tech, also associate director of the NCFL. And then I wear hats too as the associate director for innovation and entrepreneurship for our Nano Earth Center and the National Nanotechnology Coordinated Infrastructure. So it's a mouthful, but it's basically just to say I'm pretty deeply connected to nano infrastructure at Virginia Tech and beyond. And this word infrastructure is really an important one these days. We're talking about trillion-dollar bills coming down from Capitol Hill, and it's because infrastructure plays such an important role in our lives. And I think we all have some connection to infrastructure, whether we're aware of it or not. At Virginia Tech, we've been blessed with wonderful infrastructure. This is the Virginia Tech Smart Road it's a big part of our transportation infrastructure supporting our institute like VTTI, the Virginia Tech Transportation Institute. We also have some new infrastructure coming online. This is the drone nest out in Christiansburg, Virginia, where they're actually launching home-based drone delivery. So these drones will be equipped with goods, small goods that can be transported easily by these drones and flown to locations all across the Christiansburg area. So this is really cutting-edge infrastructure that's supporting unique innovation that's happening not somewhere else, but right here in our own backyards in the New River Valley and near Virginia Tech. Also, I've got to give a shout out to our host, the Virginia Tech Corporate Research Center, and the innovation infrastructure that they've created. And I call it award-winning infrastructure, as I think the Association of University Research Parks named them one of the top corporate research centers. And having had a company here now for going on 13 years, I can actually 14 years, I'm sorry. I can attest to the remarkable infrastructure that our Virginia Tech Corporate Research Center provides. And there's some interesting, one of the key points of the talk that I want to, of this whole session today is really to drive home this concept of game changers and to emphasize the point that game changers and game-changing innovation requires game-changing infrastructure. And that's something that we have a lot of here at the Virginia Tech Corporate Research Center and around Virginia Tech. One piece of game-changing infrastructure that I want to highlight today, and particularly its connection to quantum, is our Nanoscale Characterization and Fabrication Lab, which you see, hopefully can see my attendee images are overlaying this, but the circled area that you see there just behind Tech Lab and the Life Sciences building, and you see VCOM here in the foreground, this is the Nanoscale Characterization and Fabrication Lab. And this is what that looks like up close. There's plenty of parking out there. So for the folks on campus who are struggling, this is a wonderful place to go and visit because you can actually find a parking spot. So that's our VT NCFL. And what I want to communicate to you about what the NCFL is, it's an observatory for materials discovery and innovation. We know what we use observatories for, and we know the beauty and insights that they bring to us. we're not as familiar with these materials observatories and the beauty and things that they reveal to us. And this is kind of what that looks like. It's not a beautiful night sky, but these are actually gold nanoparticles that you see here. And these are atomic columns comprising those gold nanoparticles. And you can see the scale bar here at 5 nanometers. This is tiny. This is way smaller than, for example, the COVID-19 virus. This is a tiny scale that's almost unimaginable. And the tools that we have here are really important for allowing that kind of work to take place. I call this game-changing infrastructure because of the type of game-changing innovation that it produces. And this was a paper in Science published in 2017 that highlighted the fact that papers in nanoscience and nanotechnology, material science, and biomaterials were those that were most closely linked to patents. So this isn't just fundamental research that's happening. This is research that's been translated into patents and economic value that then translates into economic growth, jobs, new companies, and hopefully an improved quality of life. If you look at our region, this NCFL infrastructure has been an important part of state and regional game changer efforts. So at Virginia Tech, it's supported about $500 million in research since 2006. That's between 2006 and 2019. It's also been an important cornerstone to some of the companies that we know and love in our area, companies like Luna, Nanosonic, and Meld, formerly Polymer Solutions, of course, Jefferson Lab, and my company, which I shamelessly tout there as benefiting tremendously from the NCFL over this time period. It's important to realize that. And one of the probably one of the most exciting and transformative projects that the NCFL helped us secure at Virginia Tech was this center called Nano Earth. And what Nano Earth is it's one of 16 different nodes comprising the National Nanotechnology Coordinated Infrastructure. You see the node sites there in green and yellow dots. They're scattered across the country at some of our nation's premier nano capable research institutions, and Virginia Tech is a proud member of that. And we're being supported at $5 million over 10 years to enable discovery and problem solving at the Nano Earth interface. And this is our team. Just a quick shout out to those folks who have been so important to what we do at Nano Earth. I can't name them all, but you see them there. And these are faculty and staff who really make Nano Earth happen and allow this discovery and observation to occur at the Nano Earth interface. And what I wanted to do today, before we get into Dr. Meritzbacher's talk, is to let you hear quickly from Mike Hoschella, the founding director of Nano Earth and our current director of user development, as just a case study. So this is about an 8.5 minute long clip that I wanted you to hear. And we'll go ahead and play that for you. And Celia, I'll ask you if this doesn't start cleanly, just please yell at me and we'll undertake alternative measures here. So bear with me, folks, and enjoy the video.
My name is Michael Hoschella. I'm a University Distinguished Professor Emeritus at Virginia Tech. I am a nanoscientist, but my fundamental nature as a scientist is the earth. I am an earth scientist since I was in high school. I was always fascinated with the mountains, the oceans, rivers, the sky, what I saw in the sky, things that I saw in nature. When I came to undergraduate school, actually at Virginia Tech, I was an earth science major, a geoscience major. And when I went to Stanford for my PhD, it was the same thing. But over all of those years, 10 years actually, a whole decade, I spent just as much time reading chemistry literature and physics literature and math, but still interested in the earth. And despite what most earth scientists do, which is to study mountains and oceans in the atmosphere, I decided that it would be more interesting for me personally to study the very small, things that we couldn't see with our unaided eye, and things that were so small that they would perhaps have interesting properties that drove the bigger parts of the earth, that influenced the bigger parts of the earth. And as a result, in graduate school, and actually even in undergraduate school, I became interested in the very, very smallest things on the earth. And so over the decades, I morphed into a nanoscientist. And now that's what I'm known for at Virginia Tech in the United States and actually around the world. For better or worse, some people say that I was the very first nanoscientist in the earth sciences. And I'm very proud of that, actually. It was an area that was completely wide open for study. And I hope I took advantage of that properly back 40 years ago when I started this. It was a lonely world back then because no one in the earth sciences did what I did, but that's not the case now. And I have lots of company, lots of people that teach me things instead of me teaching just them. And it's just been a great, great career. As I was going through my career decade by decade, when I got to maybe my last decade or so, I thought it would really be a good time to give back to the scientific community and to give back to society. After all, they supported me for many decades with a lot of research money from funding agencies like the National Science Foundation and the Department of Energy, which I'm personally most grateful for. Now, what can I give back? And so I felt that if we started a center here at Virginia Tech, a center that we named Nano Earth, we could give back. So how would we do that? Well, we would get a large, here we go with the money again, we would get a very large grant, millions of dollars, to hire a staff to help the field of environmental nanoscience and nanotechnology grow and prosper, not for ourselves, but for other people who needed our expertise. So to make a very long story short, we did get the funding. We did start Nano Earth. It's been going down now for 4 years, and we think it will go for 10, and hopefully another 10 past that. And we have clients from all over the United States, and in fact, all over the world that come to us, as well as Virginia Tech people who are interested. And we serve them by solving their nano science and engineering and nanotechnology problems. A lot of them have very little expertise in nanoscience. They're great practitioners of other sciences, but they know that nano is a big part of what they're doing, but they don't know exactly how or what to do with it. And that's where we come in. So we actually serve this outside and internal population to solve their nano issues. So we work with other universities, community colleges, four-year colleges. We work with high schools. We work with elementary schools. We work with national laboratories in the United States and around the world. We work with companies, big and small, companies you've heard of and companies you would have never heard of because there are only 5 or 10 people working for them. But they have important problems too that are nano related and typically nano environment related. So that's what we do for a living now with Nano Earth. We have an incredible staff of professors, other scientific staff, of administrative people that make the whole center work financially and with our communication to the rest of the world. And together, we hope, and this money comes from the nice National Science Foundation, we hope they're getting their money back plus. And that's what NanoEarth is. We're really proud of it. One of the problems with nanoscience and nanotechnology from the viewpoint of the people who do that are that the instruments that you need to study things this small and to do such unusual or to have such unusual properties when you're trying to measure those properties of things that are so small, the techniques that we use, the instruments that we use are really expensive, typically. So for example, this microscope in back of me is called an electron microscope because a light microscope uses visible light, so you can see things looking through something that sits on a bench top. This is an electron microscope. So instead of using visible light to see small things, it uses electrons to see small things. And it does that in a high vacuum. And it does that with extraordinary electronic precision. As this column that you see in back of you is accelerating electrons to near the speed of light to go through your sample and to image it into images that you see in back of me. And to buy one of these microscopes is painful because they cost at least $1 million and as much as $7 or $8 million for one of these microscopes. Now, a lot of university researchers, a lot of companies don't have that kind of money to buy their own pieces of equipment like this. So in effect, NanoEarth buys these instruments for them and does the research for them to understand their issue at the nanoscale. So these instruments are very expensive. They're really hard to maintain. They're really hard to use. We have the experts to do that. That's what NanoEarth exists for. And that's how we can help people here at Virginia Tech, around the state, around the nation, and around the world.
So just really appreciated Mike taking time out to chat with us. This was done right before the pandemic happened. It was one of the last things that we got to do together as part of an interdisciplinary team with Justin Perkinson, Tanner Updegrove, and one of their undergraduate students. Let me see here. We're going to move on.
My name is Mike.
Now, the interesting thing is the NCFL has enabled this important NanoEarth capability to occur in our area, but we never rest. So we're always looking at the next thing, right? So part of what Virginia Tech is in the process of doing now, if you look at the Vice President for Research and Innovation, Dan Swee's vision, is to look at 4 different frontier areas on campus. And one of those frontier areas is the quantum frontier. And we are gearing up now as we speak. Folks all over campus are looking at how do we support that frontier? How do we enable the next quantum startup? How do we enable the next major research award at Virginia Tech? And so there are a lot of people looking at this, and we're certainly looking at it from the NCFL's perspective too, is how do we take the equipment and capabilities that we have now that are serving programs like NanoEarth and bring those up to speed so that they can support exploration at the quantum frontier. And to help take you on this journey, I am no quantum expert. And so to help take you on this journey, it is my privilege to introduce to you Dr. Celia Merzbacher. And Celia serves, she has an extraordinarily impressive background and resume, and I won't cut into her time going through all that, but Celia in her current position serves as the Executive Director of the Quantum Economic Development Council, or Consortium, I'm sorry. And how I met Celia was it was one of my first experiences as a young nanoscientist. And I think that Celia was working at the Office of Science, the White House Office of Science and Technology Policy at the time. And I just remember Celia she was this rock star. And I was this naive nanoscientist coming out of industry. And she was so gracious and so helpful. in this early stage of understanding nano and how to manage health and safety risks of nano and that sort of thing. And I was just always grateful for the time that she took with me at that point in my career. And so I was thrilled when she agreed to speak with our group today on quantum as a game changer and building on this nano foundation that we've established. So Celia, I'm going to exit out and turn it over to you to share your slides, and you can take it away.
Thank you, Matt. And it's really a pleasure to be here. I will go ahead and share my screen. So thank you very much for the opportunity to join you. And I'm talking to you from Alexandria, Virginia, just down the road from where Virginia Tech is building its innovation campus. So I feel very close to you, even though I know you're in Blacksburg and the NCFL is in Blacksburg. What I wanted to talk about today is a little bit about quantum, equation-free, not a heavy physics introduction, but just to give you a sense of what it's about. And what it's going to be useful for. I think we focus a lot on the science, especially in the university and research community. But at the end of the day, I'm with an organization that's really interested in making something practical out of all of that science. There are challenges for R&D, and they're very much in the nano domain. So I'll talk a little bit about those and how QEDC and Virginia Tech, who is a member of the consortium, will accelerate progress. And in the course of doing that, will hopefully benefit the economy. Economic development is our middle name at QEDC. The nation, there are national security aspects of quantum, and society. So with that, I will see if I can advance my slide here. There we go. So quantum feels very new, and it reminds me a lot of the early days of nanotechnology when Matt and I first met. And in fact, the National Quantum Initiative is modeled in many ways after the National Nanotechnology Initiative that was almost 20 years ago now. But quantum is actually a field of physics that's been around for quite a long time. It's really based on theory that was developed by people like Einstein and Planck and others in the early, very early 1900s. And there are practical applications of the theory that was developed by them and the experimental advances that were made in the 1900s in the mid-century, mid-20th century. And we sometimes refer to that as quantum 1.0. And that involves things like lasers and MRI machines, and even the semiconductor transistor is an example of a technology that was developed thanks to the understanding of the quantum behavior of materials. But in those examples, we're looking at what we think of as ensembles of things, light or matter in sort of groups of objects. And what we're excited about today, and what's really based on advances in the last 20, 25 years or so, is what you can think of as quantum 2.0. And that really is based a lot on understanding materials at the nanoscale, at the lengths of atoms and subatomic distances. And some of the examples of applications of the ability to control matter and measure it at the nanoscale include things like atomic clocks or improved atomic clocks, new kinds of sensors, super secure communication, and of course, quantum computing, something that is in the news quite a bit. And I'll talk a little bit more about all of these with a bit of a focus on quantum computing. So I think this is the little intro to quantum. The things that distinguish quantum 2.0 from quantum 1.0 include this idea of superposition and entanglement. And these are quantum behaviors that are observed, again, at these nano length scales. They're really all around us. Matter, when you get down to that scale, has these behaviors. And that allows you to do things that you can't do with larger scale objects and features. I think we're all sort of familiar with the concept of the digital world, the idea that classical computing and the digital information technologies rely on converting everything to ones and zeros. And in fact, the world is not a 1 and 0 kind of place. It's a very gradient kind of place. Temperatures change incrementally up and down. A lot of things are what we call analog. Quantum bits or qubits are both ones and zeros. And so there's a superposition of these states that allows for more information to be stored and managed and manipulated than a 1 and a 0. And so certain problems that scale and become impossible to do because they grow too large using just ones and zeros are manageable using qubits because of this phenomena. So in order to create a qubit, you need some kind of a system, I'll use that word, that has two energy levels that you go back and forth between. These are the ones and zeros, essentially, of the qubit. And those systems there are very many different kinds of systems that exhibit that behavior. On the left here, I show a simple electron. As you probably know, electrons have spin, and you can just call it up or down or 1 or 0. And you can go back and forth between them by putting energy in or taking energy out. You also have examples like atoms with multiple electrons in their orbits around the nucleus. And again, you can move electrons between different orbitals, different energy levels, and you can create a qubit that way. And it turns out that there even are structures, superconducting structures, that behave like a quantum bit, a qubit, even though they're much bigger. And I show an example and a picture here on the right. You can see the 1 micron scale bar. So that's a much larger physical structure. You're no longer at the scale of the atom, but it still is behaving like a multi-energy level system with these energy levels that you can go back and forth between, and you can use it as a qubit. So what makes a good qubit then? We've got a lot of different ones around. Why would we choose one over another? Well, first of all, you need to be able to put it into the energy state that you care about, control and measure its energy level. So you need something that you can access that way, that you can initialize and measure. It also needs to remain in this quantum state long enough to do something useful with it. And we call that the lifetime or the coherence time of the quantum state. So the longer the coherence time, the better. It needs to be something that can be scaled, meaning if you want to have a lot of qubits, you need to be able to connect them to each other and do something useful, a sort of circuit, if you will, using many qubits. And finally, at the end of the day, it needs to be something that can be manufactured. So what are some of the qubits that people are looking at using for quantum systems? Well, I show several of them here. At the top left is an image from some work done at the University of Innsbruck in Austria of trapped ions. There's a lot of work that's been done at places like the University of Maryland and other universities. And this is what's being used by companies like IonQ and Honeywell as the basis for the quantum computers that they're developing. You can also use a neutral atom, so not a charged ion, but a neutral atom as the basis of a qubit. Has some advantages and disadvantages, it turns out. And that's the technology that's being used by companies like Atom Computing, a startup that you may or may not have heard of, and Cold Quanta. Then you have over on the right a picture, and this is from IBM, of a superconducting qubit. And as the image suggests, this is the kind of qubit that IBM has chosen to bet on, as well as Google and Rigetti, and some others. Bottom left is a picture of silicon qubits. Now this has got some advantages in that we know how to manufacture silicon devices using semiconductor fabrication technologies. And indeed, that's the approach that Intel is looking at. And it's really based on silicon quantum dots. So very much a nanoscale fabrication process there. The next one over is nitrogen vacancy centers in diamond. And that, it turns out you can put a nitrogen instead of a carbon in a diamond and create a trapped vacancy that can be a qubit. That has some advantages. It's solid state, doesn't have to be cooled to very low temperature like a superconducting qubit does, but it's hard to connect them to each other. So that's a type of qubit that it turns out may be most useful for things like sensors or technologies other than quantum computing. And then bottom right is an example of photonic-based qubits. So that's light, which again has some pluses and minuses, and that's being developed by a company called PsiQuantum and another one, a Canadian company called Xanadu. So there are examples of technologies and applications using all these different kinds of qubits, and as I say, they all have advantages and disadvantages, and it's very much an open question which of these is likely to be the most successful. And maybe we will even have systems that use more than one of these types of technologies for different reasons. Okay, so let's get into just one of those qubits, the superconducting qubit, because it really illustrates how nanoscale the problems are here, even though a superconducting qubit is a relatively large scale structure. And so over on the left is a picture of the kind of guts of a superconducting qubit, the Josephson junction. And it's really easy to make in the lab, actually. You deposit layers of aluminum and you allow them to oxidize, and you end up with the sandwich of an insulator conductor sandwich. And over on the right is a cross section of those materials. So you can see the aluminum up at the top and the bottom, and then in between a layer of aluminum oxide. And you can see this is definitely a nano-sized feature. It has to be controlled very precisely. And it turns out while it's not that hard to deposit aluminum, even in a research laboratory, it's hard to make it really precise and clean. So this shows how much progress has been made in superconducting qubit lifetimes over the last 20 years or so. Now remember, you want to have long lifetimes in order to be able to do quantum calculations during the lifetime of the qubit. But you'll see over here on the left, the lifetimes that we're talking about here are pretty short. This is in microseconds, a millionth of a second. So 1 microsecond is here at 1, and then this is a log scale. It goes to much shorter than a microsecond, starting in around 2000. Now, here out in, this may not be up to date, but roughly our current best efforts are something like a millisecond, 10 to the 3 microseconds. This is 6 orders of magnitude of improvement, so that's huge, but it's still could be better. And what is it that is happening? Why are we able to improve these lifetimes? And what do we need to do to improve them more? So this has really been thanks to advances in materials and nanomaterials, in the design of these structures and features and their fabrication, nanofabrication, and in controlling the environment, because a qubit is very sensitive to any kind of noise, and that includes thermal noise, which is why they're generally kept very cold, but vibration, any kind of noise can jar it out of its quantum state. So you want to isolate it very carefully from the surrounding environment. So digging in a little bit more on these materials advances, and these are some pictures taken from a review that's now a couple years old, but it does a nice job of showing kind of where the sources of these problems are at the nanoscale. So over on the left is, let's say, aluminum and oxygen atoms in yellow, blue, and orange. And you have all kinds of defects that occur. You've got some hydrogen that's attached to one of the atoms. You've got things moving around. You've got dangling or broken bonds and so on. These are all different kinds of defects that create noise and shorten the lifetime of the qubit. And over on the right, it shows some of the sources of those problems, those defects. You can get these hydrogen groups that are sort of absorbed onto the surface if it's not perfectly clean. You can get, defects between the two metals that you're depositing. And then just generally things absorbing on surfaces. And Mike Ocella's a surface scientist from way back. He would appreciate this, how important it is to keep everything ultra clean. So that's really a nanomaterials issue that is continuing to be addressed. Okay, so we've talked about these quantum computers. So we talked a little bit about some of these nanomaterials challenges that are being addressed by researchers. But I'd like to just now sort of pivot and talk about why we care about these problems and why we should keep doing the research that needs to be done. What is a quantum computer going to be good for once we address the problems? Well, it turns out that the world, the natural world in particular, is very quantum in its behavior. And that's why when you try to digitize it, sometimes it's not very easy. You don't get accurate results. You have to make some assumptions. You create models instead of accurate representations or fundamental principles being the way you get to the answer. And so some of the examples here that I show are modeling molecules that could be a drug, pharmaceutical type applications. Those are usually large molecules. And as you add atoms to a molecule, the number of configurations and ways that it can be arranged, and then in turn how that interacts with the body, grows exponentially. And very quickly, after about 5 atoms, you cannot do a sort of first principles calculation using classical computing. But with a quantum computer, you would be able to. I show a picture here of a sort of complex fluid flow problem. These are very complex types of systems and important for things like weather and how chemical processes work inside of a factory, or all kinds of problems exhibit this kind of behavior. And that's extremely chaotic and difficult to model accurately. And so again, quantum computing could be a good way to approach those kinds of problems. Optimization, taking many sort of possible solutions and figuring out the best one, is a problem that quantum computers are likely to be very good at, much better than a classical computer. And those kinds of problems are all around us and in all kinds of business. So whether it's modeling a financial portfolio, or the route that the Amazon delivery truck should take, or the electric grid, and how you bring all these now more and more distributed generators of energy and users of energy on the grid into an optimal configuration, is the kind of thing that quantum computers are going to be good at. And there are other machine learning and search problems that also are being thought about. And people are already writing algorithms to run on quantum computers, even though we don't have one today, because there are simulators using a classical computer that you can actually kind of play with now. And there are quantum computers, IBM and others have made them available, but they're not very powerful yet. So we're kind of at this point right now where we're doing software research and hardware research at the same time, and that's really important. And so we need not just the physicists and the people in the lab, but also software engineers and computer scientists to be tackling these problems. So there's a lot of hype around quantum and quantum computing. And I just found this figure from 2020 by Gartner. You may be familiar with the Gartner hype cycle, which they started decades ago and update every year. And now they actually have separated it into several hype cycle graphics like this one. So here you can see quantum computing is right at the top of the Gartner hype cycle, which goes from some kind of early stage where some discovery is made and there's an idea for something that might be useful and innovative. And then it gets, expectations get very high, and the hype it goes up to an extreme level, the peak of inflated expectations, after which there tends to be this sort of sugar crash that happens. And you get the trough, what they call the trough of disillusionment, followed by the slope of enlightenment and ultimately the plateau of productivity. So you can go back, and it's sort of an interesting exercise to do and see how certain technologies have traveled through this cycle. Not everything does, but I just wanted to point out that we are kind of at this peak of inflated expectations. And so I hope I'm able to convince you today that there's some real basis for the excitement around quantum, but also maybe set the expectations appropriately. I also will point out that this is the only dot on this hype cycle curve that's a yellow triangle, which down below indicates that their estimation is that it's going to be more than 10 years before this technology is ready for commercial use and gets out here to the plateau of productivity. So that's longer than all the other things that they show on this curve, and that's something to keep in mind. So how are we going to get from where we are today to that future when quantum computers are going to be actually useful? Well, one way to sort of think about it is to compare it to the history of the semiconductor. And I show here a famous picture of the first semiconductor that was demonstrated in the lab at Bell Labs in 1947. And there's nothing here for scale, but I think you can grasp that this is a macroscopic object. And it is just demonstrating the semiconductor behavior of a piece of germanium, I believe, in this triangular shaped part in the middle. So fast forward from that to a modern wafer with semiconductor transistors that are measured in nanometers. And you can appreciate the technological advances that have occurred, but that took decades to get from this first demonstration to where we are today. And in order to accomplish that and be able to manufacture these semiconductor wafers and all of the technology that goes with it, a lot of processing and materials understanding and advances had to take place. So I just show some of them here, and some of them are using systems not too different from the one that Mike Ocella showed, his electron microscope. You have molecular beam epitaxy and these deposition techniques that allow you to deposit these structures that are measured in nanometers. So we're a lot closer in some ways to the picture on the left than the one on the right. And it's going to take a lot of research and development to make progress, and it's going to take some time. Another point that I'd like to make is that for many of the applications of quantum, we're going to need to get it out of the lab and into an application where it needs to be more compact. There's an acronym, SWAP, that some of you may or may not have heard, which stands for size, weight, and power. And sometimes you add a C for cost. And ideally, you want to reduce all of those if you're going to make something that's going to be sold in large numbers, manufactured in large quantities, and used by system developers for all kinds of uses. So the picture that I show here is a lab, many physics labs. I'm sure you can go into a lab at Virginia Tech and see a scene that looks very similar to this. You've got all of these lasers and optics on an optical table. It's all in a very controlled environment, and it takes up most of a room. And this is actually a picture of an atomic clock, a very accurate atomic clock. Obviously, it's not something you can hope to practically use in any situation outside of the lab. What you really want is something more like this. And I don't have something for scale here, but it fits in the palm of your hand. And this chip scale atomic clock is the result of a DARPA program that said, we want to shrink, we want to reduce the swap of everything on that optical table into something that's the size of your hand. And it was a very successful program. It's not as absolutely precise as the lab scale or the big picture on the left, but it's good enough. And you can obviously put that in a lot of systems. And it turns out the main customer for these chip scale atomic clocks is the oil and gas exploration business. They use it for undersea navigation, position. You can get your position very accurately using an atomic clock. And the people who do deep sea oil exploration have taken advantage of this technology, as well as some of the customers that DARPA presumably was interested in. So how do we bring together all of the parts of the innovation ecosystem that need to come together in order to take the results of all the research that's being done? And the US government under the National Quantum Initiative is indeed funding a lot of research these days. How do we get that out into practical application? Well, there's the whole sort of research part of that ecosystem, researchers, funding agencies, educators at universities, creating the workforce of the future. And Mike Ocella spoke about that role for Nano Earth. But you also have these other parts that need to be engaged. You've got national labs, you've got industry, both software and hardware developers in industry. You've got investors making investments in startups and small businesses. And then you've got manufacturers and ultimately end users. And you really want all of these pieces of the ecosystem in contact with each other, aware of what each other needs, knowing what an end user wants to be able to do drug discovery, for instance, can really help the software algorithm developers as they try to make applications that are going to be actually useful. Well, QEDC, the Quantum Economic Development Consortium, brings together all of these stakeholders. QEDC was called for in the National Quantum Initiative Act that was passed in 2018, and it's funded in part by NIST, but also by all of the members. And today we have more than 100 companies, about 36 universities, of which Virginia Tech is one, several of the national labs, as well as others. And we interact closely with government agencies. So we really bring together all of the components. We're very much industry driven, but we recognize that all of the parts of the ecosystem are critical at this point because it's such an early stage technology. And so you need the researchers working closely with the innovators. So the mission of QEDC is simple: enable and grow the quantum industry in the US. And the industry includes the supply chain, the end users, and all of the folks in between. And we have groups of members that have come together and are working to identify enabling technologies. Those may be for photonics or for ultra-low cryogenic systems and so on, as well as the quantum-based technologies. We are focusing a lot on the supply chain and on the workforce. And the universities that are part of QEDC are critical to that workforce development. As I said, we really are about connecting people and organizations. So we work closely with the government and connect government agencies to the right part of the ecosystem when they need that help. And we facilitate collaboration because a lot of the business of quantum today is in research, and the government funds research. There's a natural sort of need to connect all of the industry and government and academic performers. So I just added this slide this morning because, and it's probably hard to read, but we did a survey last year of our quantum industry members, and we asked them, what jobs do you think you're going to be hiring to fill in the next 5 years? And for each job that they indicated, we had a big menu of jobs that we created based on advertisements for positions, of which there are hundreds today. So when they checked one of the jobs, then we asked them, for that job or work role, what skills do you want the person to have when you hire them, and what degree, both level and field, do you want them to have? We're about to publish an analysis of the survey results, but I just wanted to share with you this picture, which shows the most frequently checked jobs, or actually skills that the quantum employers, quantum industry hiring people are looking for. So for those of you who are either students or are associated with educating students, this is really useful information, and that's why we're going to be publishing it and sharing it widely. Not surprisingly, some of the skills that people are looking for may be unrealistic. Product development, there's not a lot of experience in product development of quantum products today, but and software development. But as you go from left to right, fourth from the top is quantum science, which is really nanoscience in a lot of ways. So chemistry, physics, surface science, materials, that's one of the top skills that employers are looking for. Algorithm developers, several in the top skill sets are more software related, but then you get to device testing and characterization, squarely on the NCFL's list of capabilities and what you're teaching people to do. And as you go from left to right and just scan these positions, many of these skills do not say quantum. And so a student that's coming out of a traditional electrical engineering or materials science program is probably well equipped to get into this field. And it would certainly set them apart if they had just a little bit of quantum knowledge on top of that. But you don't have to go and get a PhD in physics. In fact, when we asked what degree do you need, more than half said they wanted bachelor's or master's degrees, not a PhD. So there's enormous demand, and the variety of skills that are needed are broad. And I think that Virginia Tech and the NCFL, the whole nano infrastructure, is going to be critical to supplying this workforce. So I'll just wrap up by saying that quantum is a game changer. There's some pictures here that show the kinds of applications that are envisioned, and they're not just quantum computers. There are quantum sensors that might go into aircraft and automotive, remotely operated or autonomous vehicles. The picture in the bottom center is a wearable kind of helmet that has nano sensors for detecting brain function. You don't have to put the patient into an MRI machine. You can just put this thing on. It might work better for children and so on. And then there are cybersecurity and computing related applications as well. So it's a very exciting time. It's a great time to be a researcher in many fields of science and engineering, because they're all going to play a role in realizing these applications. So with that, I want to thank you all. And I really enjoyed having the opportunity to talk to Matt before the meeting today, the event today, and I'm happy to take the last few minutes if there are any questions that any of the folks who are in the audience might have. But thanks, Matt.
Celia, thanks so much. That was wonderful. I'm going to go through here. It looks like we need to allow our participants to talk. So I'm going through each of our attendees names here and allowing them to talk. Looks like everyone's on mute. If someone's not on mute, I just want to make sure that you are aware that you're now able to talk. And I see some folks on here who are good friends and colleagues of mine, Dr. Hill, Jason Jones. Really appreciate you folks joining us. So if there are any questions, feel free to unmute yourself and ask Dr. Merzbacher, or you can add it into the chat.
And while we're waiting for folks to think of questions, so I mentioned that Virginia Tech is a member of the QEDC. What does that mean from a practical point of view? Well, it basically means that if you're affiliated with Virginia Tech, you have the right to attend events, to participate in QEDC, we have this afternoon a student e-poster session where 3 or 4 students are going to be giving presentations on their research, and our industry members show up and meet the students that way. So we connect students with opportunities at the companies, and we are always trying to, make the companies aware of what's going on at universities. We had a session last week where we highlighted, I think, 3 or 4 of the NSF centers. So we're always looking for ways to connect these different parts of the ecosystem, and students and faculty are an important part of that.
Thank you, Celia. It looks like we've got a thank you there, but not too many questions. So I actually have I have one for you. This is very important to me as we look at this from a university perspective. Can you, as we think about universities in particular, are there any university research centers around the country that you have seen that really stand out in quantum? And can you comment on, if one of those comes to mind, can you also comment on what it is about that university or even industry player that what is it about them that makes them stand out in the quantum area?
Yeah, I mean, it's a combination of, I sometimes like the word competencies or capabilities, which means not just having the infrastructure and the facilities, but also the people who, are kind of at the leading edge. And there are a number of universities that I think are among the top tier in both of those areas. The University of California at Santa Barbara, which has an NSF center called the Quantum Foundry and is focused on nanomaterials, both fabrication and characterization. And they have historically had a very strong physics department, so I think they're building on that. In other cases, you may be building on expertise in areas like cybersecurity or more software-based aspects. And I think software is a discipline, or not software, but computer science, let's say, is a discipline that I'm sure is working in areas that are related to quantum control and quantum computing. But in that skills chart, quantum algorithm developer was among the highest sort of skills that people are looking for. And the ability to program quantum computers is not just a matter of migrating an existing code to a new platform. Quantum computers are going to use an entirely different sort of approach or methodology for performing computation. So it's really an open area, and being able to sort of at the same time that you're developing the hardware, think about the software, I think is going to be really important. So this is very broad, and part of the reason I included that chart with all the skills was intended to show that there are a lot of different fields that are going to be critical. And so some of the programs that are out in front, I guess, include not only physics departments, but engineering and computer science departments across the country, really.
Excellent. We've actually had a couple of questions trickle in, so we'll kind of move through them. We've only got a couple of minutes left, and I want to be mindful of the sessions that occur on the back end of us. One of which I think Dr. Hill has a session at 1 p.m. just for those who are interested in joining. But Dr. Hill actually submitted our first question. He asks, what do you think will most likely be the first breakthrough quantum-based product that the general public would be beneficiaries of in some way?
Well, predicting
So
is always a little risky,
ball.
but I think that there's so much attention on quantum computing, but there are quantum sensors that are nearer term. And I showed that picture of the chip scale atomic clock, which is something that the reason DARPA was so interested in it is because a clock, a really, really precise clock, allows you to navigate successfully even if you don't have GPS. And so the military envisions that they might be in situations where they don't have access to GPS and they would need that kind of capability. But it can also be used in commercial applications for similar purposes. I think that some of the biomedical applications are really interesting. The ability to measure things in the brain and in the body that you can't measure at all is, I think, going to open up a lot of potential. And there's a lot of interest in those sensing applications as well. So I think that it's still a bit of a leap, or it's going to take some time to get from the research in the lab out into these applications. But the optimization type problems, again, you're not going to have a quantum computer in your cell phone anytime soon. There are the IBM and Google approaches require ultra low temperatures, and they're likely to provide those quantum computers via the cloud. And so those are the kinds of sort of high performance computing. It's going to complement and add value to what we can do with a computer today, but likely to be accessed via the cloud and initially for research purposes. But I think, that's how many things start at the research stage, and then they find applications. And I will make this prediction. The biggest application is likely one that we haven't even thought of.
Great answer.
We run past the top of the hour. Did you want to run through any of these others?
We have a couple of questions.
Unified field theory.
Yeah, we have a couple of questions from Eric and Mary. And either if you would like to answer them quickly now, or we can shoot them a response after, whatever your preference would be. We don't want to keep the group past the hour much, and I know they might not be quick answers here.
Yeah, I'm not a physicist, so I'm going to pass on the question about the quantum, the unified field theory. But on the question about infrastructure investment, just like nanotechnology, a lot of the research type equipment is fairly esoteric, it's expensive, and in fact, much of the same equipment will be needed. So I think all of the labs like yours are well positioned to support quantum researchers who I'm sure are probably all around. And it's not just a matter of relabeling nano as quantum, because it's really sort of building on that foundation, and there are some distinct differences. And so some quantum learning is useful to be able to support that research, but there's a question here. The questioner, particularly as relates to computer science and software, I think I mentioned a little bit about how important I think computer science and software are going to be. I didn't explain that because quantum qubits are so fragile, they're kind of noisy, and there's a lot of error in a quantum computer today. And so one of the big challenges is, how do you correct for error? And as we steadily try to improve the situation with respect to how noisy these systems are. At the same time, computer scientists are working to try to come up with clever ways to do error correction. And that's a really tough computer science problem, but incredibly important. It will open up noisier qubits to being practical sooner. And so there sort of is parallel efforts going on the hardware side and the software side that are going to be critical.
Excellent answer. And with that, I think we'll go ahead and wrap up. Thanks to everyone for joining us. Thanks, Celia. Wonderful talk. Really appreciate you joining us. I think we'll have a recording of this. Hopefully it'll be available on the CRC webpage. And again, thanks everyone.
Good luck with the rest of the GameChanger. Thank you.
That's right. Bye-bye.